Okay, so today we're going to be talking about an introduction to what we mean by machine learning, what the concepts around machine learning are, and some ideas about how we've applied machine learning at KieranTimberlake. So at KieranTimberlake, every time we talk about a really novel practice within architecture or something that's happening in the world that we think can or should be potentially applied to architecture, we ask a couple really key questions. And those questions are, is it worth pursuing? Is it something that we think is going to provide additional value within the services of architecture and AEC? Is it practical? Is it something that we can apply to the work that we do now in a way that helps or improves something in a noticeable fashion? Is it even possible to do? And more specifically, can it assist with AEC workflows? Is it something that saves us time, saves us money, saves us effort, makes what we do better? And so over the last little over a year, we've been asking these questions about machine learning and really starting to dive into it. So in that deep dive, we started off by saying, what are other people in our field doing with this? Because machine learning, as much as it is in the media, it seems like constantly, it's something that is still fairly novel within AEC, but has also been around for a long time. Its history goes pretty far back in the computational world, back into the 1950s and 60s. So how are people doing that now? Well, smartvid.io, which got bought by Autodesk sometime in the last year, is doing machine learning applied specifically to the topic of, oh, the video doesn't want to play. Bummer. Is doing some video recognition within their construction sites, and that's how they're using machine learning, is essentially doing video analysis to monitor things like security and safety. You can think of ways that a contractor might be really interested in being able to make sure that when they have a crane, they have a perimeter marked out around that crane that is the appropriate size and at the right time. And as an architect, it's something that you could think about as, it's a way for me to not necessarily have to be there in person for the entirety of CA, but I can monitor what's going on the site and actually have something else doing that monitoring for me, other than just the GC. And I can determine when I actually do need to be there in person. So I can have a video recognition software that's looking at the changes that are happening and notifying me when, hey, it's hit this other point that you previously identified as this is a major thing, right? So you're there for the pour, you're there for whatever major erection is going to be happening, right? You're there for them putting the steel into place. So you can identify what the steps are that lead up to that, and no matter what delays and everything else that might be happening, this potentially could allow you to be smarter about the way that you're going about your CA. WeWork, now that they have, I don't even know how many thousands of properties, has been applying machine learning to a lot of the data that they get from what they've been doing. Things like, which variations on a conference room do people tend to prefer? Do they prefer them when they're smaller? Do they prefer them when they're larger? Do they prefer them when they're in a corner location versus a central location? How do they prefer certain colors? Do they tend to prefer certain layouts, right? All these different characteristics of those conference rooms that have now been arrayed across those thousands of locations around the world, and saying, are there certain design characteristics that those more preferred conference rooms tend to have in common? Is it just that people like to walk the shortest amount down the hallway, right? What might they have in common, and how can we tell which variations people tend to prefer? And start to look at that in a rigorous way that's not just tinted by our human biases. Similarly, what type of maintenance tickets are most frequent, right? This is something that's looking at submissions for maintenance requests, which are done essentially manually, and therefore doing a simple in and out program that just says, oh, people most frequently, say that the plugs are broken. Well, how do you figure that out? Because some people are going to say plug, some people are going to say outlet, some people might say the power in the room doesn't work, right? There are lots of different ways that we could submit that same request when we're using natural language. And so using an algorithm that allows for that kind of knowledge to come to the forefront. Autodesk, as we all know, puts all kinds of stuff in the background of all of their software, but one of the big things that they've been pushing recently is the application of machine learning on the back end to do what they call design assist. So something like a search engine for three-dimensional geometry. So rather than necessarily having to go through and tag every single one of your families, being able to already identify what type of object that thing is. So is it a chair or is it a table? Anybody in the room can look at that and they'll know, a table has certain characteristics and chairs have other characteristics, and usually it's not that confusing to figure out. But when you think about actually programming that, what is the difference between a chair and a table? Well, sometimes a chair has arms, sometimes it has a back, but sometimes it doesn't. And how do we identify the differences, right? So thinking about how we can start to train our computational tools to have some of that basic awareness of things that we would have so that they can help us better, and so that it's less about making sure that someone doesn't put a typo into the metadata and call it a tablet, tally instead of a table, right? Because they switched the L and the B. But rather having the computer being able to identify that, that gets around some of those human errors so that things like our Revit libraries potentially could become more accessible. They're not at that point yet with this particular technology, or at least they haven't put it into Revit yet. But it is something where, all of us who try and keep our BIM libraries clean, or anyone really trying to access a BIM library, can see really quickly where this could come in handy really fast, because trying to sort through all of those families, especially if you keep an archive of all the additional families that you make within each of your projects, starts becoming really unwieldy just doing it by file name, right? Other ways they're doing it is they're integrating it into the backends of software to do some of that calculation work that, yes, we're trained to do, but is just kind of busy work in the background. It's not the fun stuff. It's not the stuff that people get really excited about coming in and doing. And so essentially creating a workload assist in the background so that the computation is acting as a design partner to you, to take some of that mental load off of you, to free your brain up to work on the stuff that computers aren't so good at, things like intuition or creativity, right? Proving Ground, we'll talk more about them later, and we have talked about them in the past as well. They're the makers of the Lunchbox package within Dynamo that we've talked about how awesome it is previously, a few months back especially. But they've been doing some work into this and looking specifically at ways that machine learning could be applied within architectural projects. So things like space identification based off of geometrical properties. So you could think of this as being something that could go through and potentially label your room types for you on a schedule. And now you'd probably have to go back and redline that and correct a few things, because the difference between a mechanical closet and a janitorial closet is not necessarily evident from geometrical properties, but it could save you a bunch of time because, as we all know, Revit's super slow, and doing things like putting labels on stuff is not really anyone's first thought when they wake up in the morning about what they'd like to do today. So again, trying to think of ways that this can take some of that load off of you. And similarly, using it to predict what type of furniture should be arrayed in that room, right? If it's a bedroom, there's a different set of furniture that you're generally selecting from than if it's a living room or if it's a conference room. and starting to identify and filter down the types of furniture that you'd be selecting from and the number of pieces that you might need based on the geometric properties of the room, right? So a larger conference room, you're going to put a different kind of table in there, different number of chairs. Smaller conference room, fewer. Then questions like what type of facade is expected on each face of a building massing? If you're working in a firm for a very long time, you generally know, okay, our northern facade, generally that's going to be a curtain wall. If it's south facing, we're going to want more of a punched window approach because, you know, we've learned over time that that tends to be more energy efficient. Or, you know, flip them around, however it is that you happen to do this at your firm. But if you have a new employee coming in, they don't have that embedded history in their head, that knowledge over time. But if you were to input hundreds of buildings that your firm has done, then based on the orientation and the program and the building type and the facade area and the general performance characteristics associated with those facades, over the history of the firm, the machine can now help identify, okay, it's really likely that actually, given your firm's design track that you usually take, that this would be curtain wall or that this would be an opaque brick assembly, right? So starting to think about ways too that we can start to almost level up introductory designers to a higher level based on embedded knowledge rather than necessarily requiring the time of a more senior person to sit with them and be like, no, actually, you know what, this firm, we would never do something like that. So again, it wouldn't design the building for them, but it might give them a good first pass to then show someone else. So these are all some really interesting designs and really interesting applications, but really, what is it that we're talking about? What is machine learning and how is it different from artificial intelligence? This is a really important question to ask, actually, because in media, even in some popular scientific media, a lot of times artificial intelligence and machine learning and deep learning and all of that stuff just gets sort of clumped together in one thing, and the terms start getting used interchangeably. A really good way to start thinking about separating it is thinking of humans and artificial intelligence as being an attempt to recreate thought processes, right? So with artificial intelligence, there's some kind of internal processing going on based on a variety of inputs, and then you get a decision or action. And that's supposed to work in a way somewhat similar to the way that humans work. We get inputs all the time, we do internal processing, we happen to call it thinking when it's humans, and then we make a decision or action. And that processing that we do is based on history and internal knowledge, internal weighting system, processing multiple streams of data, right? And sometimes we can explain why we make the decisions we do, and sometimes it's just gut instinct, right? There's something that tells us this is the right thing, and we can't necessarily point to an exact, perfectly linear line of reasoning of how we got there, but we've made a decision or action based on that. And there's creativity, there's all kinds of things, right? What is intelligence anyway? So there's lots of different things that go on inside of our brains in order to make these decisions and have these outputs, right? So artificial intelligence is an attempt to recreate that level of complexity in processing. That can be done in lots of different ways, or at least theoretically, that can be done in lots of different ways. There's deep learning, there's functional programming, there's all kinds of different things that we can do. And one of those things that people are attempting is something that's called machine learning. So machine learning is a technique that can be applied where you have streams of input and you want an outcome afterwards. Essentially, machine learning is an attempt to tackle this idea of how do we get computationally that output or decision to be based on knowledge or based on history or a collection of knowledge from different sources of input. There's going to be a bunch of XKCD in here. It's one of my favorite comics because I'm a huge nerd. And this is actually kind of not that far. Obviously, it's parody, but it's not that far from a somewhat accurate description of how machine learning works. So we've got our data, or our input stream, that's here in the funnel. You put the data in. There's a bunch of algorithms in the middle. You can see there's some linear algebra. There's all kinds of vectors, math, and stuff going on in there. There's some lambdas. And then we have our outputs and our answers. Obviously, things are maybe a little bit more technical than having a big pile of stuff that you stir around. But in a lot of ways, this is a pretty accurate illustration. To use machine learning, what we do is we take a problem, we categorize it based on the data and the input streams, which we call features in machine learning. And then we pick a model. We try to optimize how the input streams are handled, or optimize the parameters if we're using the jargon. And then we get an outcome. And that outcome is judged based on predefined success metrics that we've determined are about right. And if we don't get the outcome we want the first time, then we go back and we tweak the parameters a little bit. We stir up that pile of data and stir up that pile of processing happening in the middle, and then we get a new outcome and a new thing to measure against the success. I love this image. This is the generic what you get when you Google image search for machine learning. You know, it's a brain that's made out of a computer chip, which really doesn't mean anything to anyone. And especially because all those lines don't really connect to anything. And anyway, machine learning, a lot of people think about it this way. It's like the machine that has a brain, and it is a brain. And while, yes, we take a lot of machine learning technical terminology from neural science, and certainly in artificial intelligence, especially historically, there was this idea of creating an artificial brain. That really makes things a lot more complicated than machine learning is. And machine learning can get plenty complicated on its own. Essentially, machine learning is a set of algorithms that use mathematical models with variable parameters to achieve an outcome. Simplifying that even further, essentially, machine learning is a really sexy name for advanced computational statistics. Now, don't leave. It's more exciting than that makes it sound. But, you know, it basically is, we're using some really complex math to try and take a bunch of data and get some stuff out that we wouldn't necessarily be able to do ourselves. And we're trying to figure out how we can train our models, which essentially is just we tweak that big data, we stir up that pile of data, and stir up those parameters in order to make our models better. And that's called Bayesian optimization, or recursive optimization, or backpropagation, which essentially are all different terms and different ways that we go back to have the machine figure out how to stir up that pile of data. So it's not us standing there with our shovel, right? Essentially, it's trying to have a smart way of making the machine do some of that statistical work to figure out how to tweak those internal parameters in order to get the feedback that we're looking for. So after it's run once, hopefully we've gotten it trained so that it's going back and it's changing its parameters internally in order to improve its outcome. And it can change those parameters, we can change those parameters, or it can be a combination of the two. So again, thinking about the way that the design works, right, it's an assist process. And in no case are we expecting that the machine has entirely replaced us. So this is a pretty typical diagram of what's called a neural network. Again, stealing some concepts from the brain. And each of these circles represents what we call a neuron. And that, again, is using brain terminology to apply to computational statistics. everyone in the room who is familiar with architects should be very used to the fact that as architects, we steal terms all the time from other people's fields and apply them to what we're doing. And there's usually some relevance, but a lot of times it's sort of metaphorical, right? And then the metaphor changes and we end up meaning things completely different from the original word. This is kind of the same thing. So each of these neurons essentially is applying a statistical process, some sort of function that we have given to it, and then it's giving an output, and that's represented by these black lines. And the output goes to the next neuron, and the next neuron is taking, in a multi-layered assembly, the next layer is taking, has a bunch of neurons in it, and those neurons are taking the output from the previous layer's neurons as their inputs. So rather than, getting the original inputs back in, they're getting the output from the first layer of input. And that's going to go on for however many layers you have inside of it. And each of those neurons is applying a process, right? So it might be that our first neuron, its process is, okay, if the number is larger than 2, then true. If the number is smaller than true, then false. And it's pushing that onto the next layer. So the next layer is getting a bunch of trues, a bunch of falses, and then maybe its rule is whichever one of those clusters is larger, that's the data that I push through. Everything else I toss, right? So there's a lot of, and those are two very simplistic algorithms, but there's a lot of different options. And the more neurons you have, the more different options are happening, the more different inputs and outputs that you have. And what's important about this is that when we're doing that back propagation or the tuning of the network using the machine or the computer, what's happening is it is going back and saying, okay, I took all this input to get an outcome, but you know what? The outcome I'm getting isn't as good as I want. So I'm going to change how much I'm listening to this neuron over here. So those black lines start becoming, instead of all being equal the way they are in this diagram, instead we get that, say, the top line up here starts being assigned a value of 0.7, right? There's a probability of 70% that this answer is the most important one that's coming in, whereas the next one, that's going to be about a 15% likelihood, and the next one down, that's more like a 5%. The next one down, well, that's more of a 2%, and so on, right? So it's a way of starting to use statistics and probability in order to say, I think this is the thing that's most important for me to get my correct answer. Another way that we can start talking about machine learning is by talking about the different classifications that we have. And there are many, many different versions of this. I'm going to talk you through some of the most basic ones in order to make everyone familiar with what the terminology is, and also to start understanding when people are talking about machine learning, what their goals are usually. And usually you can tell that by what type of terminology they're using. So if you're really focused on the output, what is coming out of that answers box, then you're usually talking about generative machine learning or discriminative machine learning. Generative meaning we are training the model, we're stirring up that pile of data in order to be able to replicate or have the machine make its own version of the thing that we're inputting. In terms of buildings, we could think of this as we're putting in all of the energy performance of every building we've ever designed, stirring it up, and the model is going to design a maximum performance building based on, all the inputs that we've given it. We're hoping the building is designing its own thing, or we're hoping the model is designing its own thing. Discriminative would say, okay, in fact, the model is just about separating things into different buckets, and it can tell the difference between things that are coming in. So if I've again, trained my model, and then I give it a new building design that we're thinking about, it will be able to tell me whether that building is going to be a high performance or low performance design. So again, thinking about it as a way of helping assist in the process rather than necessarily taking over and doing the process for us. And generally in terms of AEC, especially because it's better for the smaller data sizes, we're typically talking about the discriminative model. Other ways we can talk about the type of output are more driven by things like, well, what are these data sizes? And this is a flowchart from scikit-learn, which is the Python library that we used for our initial foray into, or one of the, to be more accurate, one of the packages that we used, one of the libraries that we used for our initial foray into machine learning. And they're a great resource for actually learning about machine learning. They have a lot of documentation. But essentially, this says, okay, if you don't have a lot of data, you need to get more data. And that's one of the big issues that we have in the AUC community, is just that our data sizes, for many, many reasons, tend to be relatively small. And part of that's because we don't share our data, which is for a lot of reasons, I know. But it's, it makes it hard to get a lot of data sizes. So then we have essentially ways of categorizing things. Again, you could think about that as being the discriminative model, or ways of predicting things or making things, right? So, and these all have different terms that go along with them. And I'm going to walk you through a couple of those in the next slide. And there are a couple that aren't represented on here because they are not really built within the scikit library. Things like anomaly detection, which is what your credit card does when it's figuring out whether or not a purchase is fraudulent, or association rule learning or association rule detecting, which is essentially Amazon's, you might also want to buy, oh, I see you've bought an egg beater. You might also be interested in this book about making eggs, because people tend to buy those together. Or, and that's where it gets really funny, is when the machine starts finding that people have bought some of the same things, but actually there is no direct association. And I think all of us have probably experienced that at one point or another with Amazon, where it says, oh, you're interested in egg beater. You might also want these hot pink leotards, right? And you're like, why? What is the link there? And that's when you start wondering about what other people do in their free time. Okay, so anyway, output. That's one of the ways that we can think about defining our machine learning. Another way we can think about it is thinking about the type of learning. So thinking about really what we as the modelers are hoping is going on. So if we know what we're hoping to get as an output, that's where we know what we don't know. That's generally the supervised machine learning. So this is us being able to go in and be like, okay, here's what's right, here's what's wrong. And then after you do your training, you get your output, right? And hopefully that output is able to sort. Then there's, is the data too complex to use? So we don't know what we need to know to probably then do something else. And that's the unsupervised machine learning. It's we don't know what we're necessarily hoping to get as an output. And a lot of times that's things like classification, sorts your data. It helps you figure out what's going on within that big pile of data that you've just been pouring in. And another one, and this is something that we have seen a lot in publicity about Google's machine learning, is training or reinforced machine learning, where we're training our model with rewards, almost thinking about it as like a puppy that gets a treat for doing the trick correctly, right? But in terms of computers, it's more like, hey, you got a score of 1, well done. Instead of whacking it with a newspaper, it's, oh, you got a score of 0. Try again. That was wrong. So again, putting it in an environment, giving it a state or an action, and then the machine will make a policy that maximizes that reward. And that's frequently when we need to figure out how we know what we know, but we definitely can identify when we're wrong. So when Google, I think it was Google, had that online algorithm that you upload in a picture and it could predict what breed of dog the picture was of, right? A lot of my friends had a lot of fun sending that around and finding out what breed all the people were that they knew, and they'd upload pictures with all of us in them, and then be like, and you're a cocker spaniel, right? Similarly, this is one where being able to identify when we're wrong is really useful, because it's also something where when you've trained the model in this way, you essentially can teach it only what it sees. So if you're training the model on lots and lots of pictures of dogs and it's just getting so many different dogs and you're giving it rewards when it gets the breed right and you're not giving it rewards when it gets the breed wrong, this could also be something that you do as a supervised algorithm rather than as training. Then when you give it a picture of a tree, it will tell you that tree is a beautiful St. Bernard, because it's never seen a tree before. It knows how to classify dogs. So every problem that it sees as being a dog problem. And that's where these things start to run into limits. So another way we can start to think about this, and essentially just relabeling those descriptions that I had before, has to do with the data that we're putting into it, and thinking about what are our sources. Do we have labels for our data streams? Do we know that that is the room name and that is the area and that is the level of opacity of the windows? Or do we need help figuring out the labels for our data streams? That's where we might use the unsupervised. Do we have a constant influx of labels for ever-changing data streams? Something like video analysis, where we have constantly changing data. We don't necessarily have labels for everything yet because we can't predict everything that we're going to see. And that's where, we need help, right? That's also frequently what's going on in the background with some of the more advanced applications of machine learning to video games, where they don't know exactly what every single person trying to defeat the boss is going to be doing, but they do know that the boss should be trying to defeat the player. So the more features you have, the more input streams you have, the harder it's going to be to train your model, and the more data points you need, right? Because if your features are, I want you to identify the breed, then if all of your features are just different pictures of dogs, that's great. That's in some ways a simpler process than if you want to identify the breed, but you're giving it dogs and you're giving it cats. So now it needs to be able to first say, well, is it a dog or is it a cat? And then say, okay, what's the breed within that species, right? The more features you have, the harder it is to train, the more complicated it gets. So why is that hard in AEC? Looking to XKCD again, what we see are a bunch of people at a dinner party having really gross sounding recipes. And the reason is because this guy from the computer sciences department has an algorithm that is attempting to make the best possible recipe, but all of the features that he has coming in include all of food, all possibilities of food, right? And the issue is that they need to have hundreds more meals in order to be able to give his algorithm enough input to be able to start solving correctly for optimization. And that's the issue that we have in AEC, because if you think about the speed with which our data accumulates, if we think of our data as being buildings that we're making, because that's what everyone really wants, is they want machine learning to be able to build a better building. How many buildings does your firm build in a year? How are you accumulating hundreds or thousands of data points if your data point is a building? And this is where us not being able to share across firms as an industry is holding us back. It has nothing to do with people being too conservative or people being really skeptical about technology. It has to do with our ability to share data. And that's why the places where we see this being applied in AEC are things like city planning, because demographic information, that's a lot of data points, pretty easily accessible. And then you can do things with that. You can train on that. You can use things with that. Infrastructure performance, energy modeling. If you are someone like Autodesk who gets lots of energy models, you can do that. But as an individual firm, that would be something that would be really hard to implement because, again, how many energy models are you doing a year as an engineering firm? So the more complex your data and the more time that you have in between your data points, the longer it's going to take you to get the data you need. And that means that puts way more pressure on the front end of how are you processing that data and how are you identifying what your features are? How are you identifying your data streams? That's going to become really important, especially if you know, we're looking at data sizes that aren't that many, and we have longer time spans. So instead of thinking about it as being a whole building, maybe you can say, okay, I'm going to break it down further. I know I need more data. I'm going to look at each facade, right? That multiplies each building by several, but again, you're multiplying each building by what, 4, 8 if you have something really complex. So your data is starting to build a little bit faster by making that one change within your data stream. But again, replication is important. More points of data are important. That's why something like feature identification with video works a lot better, because there, your data points are essentially each pixel of your video. And if you're talking about a video stream, that's a lot of data real fast, right? That's why we see things like the vid.io example as being some of the first places where this is being applied. So within Dynamo, Dynamo Machine Learning Lunchbox that we already talked about before has a package specifically made for machine learning. And they have, what's great is within that package, they have examples of data sets and how those data sets can be applied using these nodes that they've made. So you find that by going in your package manager, clicking on the little ... menu on the right hand side of the package and saying go to root directory, open the extras folder, and you'll find those scripts in there. Lunchbox is including some naive Bayes solvers in order to classify your elements within a model, regression tools which can determine fit curves and surfaces from relatively simple data. So again, translating something into points, translating a geometric component into points. So instead of thinking, okay, I have a wall, it's a plane, thinking about, oh, I have this field of points that all fall onto this plane. So able to do some different kinds of regression on that. I know statisticy words, right? They have Markov modeling, some neural networks, right? You'll notice their diagram is in hot pink with black lines. It's because I took the image of what is a neural network from their website, and also a Boltzmann machine. So this is some stuff that's really fun to play around with and doesn't necessarily require you to be able to identify the data that you can use, because they have those examples, which is great. Lunchbox also has a set of nodes for within Grasshopper. There's also something called Ant, which is based on scikit-learn, the library for Python that we used for our initial investigations. And Owl is another one. So a lot of stuff that you can start to play with and get your hands on. And each of them has some relatively clear tutorials, either on the page itself where you get the download from, or on YouTube. So other different resources for learning about machine learning. We've got some videos with either from GitHub or AU Online, Coursera, lynda.com, and then lots of documentation in various repositories. Wikipedia is actually a really great resource for this. Turns out a lot of machine science, computational science nerds edit Wikipedia. Who'd have thought, right? So really great resource there, and lots of open source options. If you're looking for something that's AUC specific, I strongly recommend looking at AU's online lectures from 2017. There were several presentations on applying machine learning within AUC. One of them is looking at optimization of HVAC, and I can't remember what the other ones were, but if you go to AU Online, you'll be able to find those. Just keyword search with machine learning. So how did we get into this at KieranTimberlake, and how is it that we're using it? Well, there are all these different areas where things are being applied, city planning, smart buildings, infrastructure design, and one of the things that we started with is where do we have enough data, right? Where are there enough data points? So one of the things we've been looking at are algorithms to just process and identify images. So in this instance, what we're looking at is a phase change material. It's wax, it melts, it changes phase, right? And trying to identify where those boundaries are between the liquid and the solid, which is actually really hard to do by eye, tracing it through and following it, and then being able to actually identify that boundary line to be able to process. Really, really hard to do manually, really, really hard to do visually, but machine learning is able to do it. And the goal of this is to be able to then use it as a way of verifying our simulation models to understand the rate at which things are melting and changing. This is a workshop that we give on understanding thermodynamic properties, and the machine learning is a teeny, teeny, tiny little part of that. But looking very much at that image processing as being something that's much simpler to do, because again, your data stream is every single one of those pixels. And what we're doing in that is essentially we're using these types of neurons. So the function within each neuron is pretty simple. It's put it to white if the pixel is above the line that we've identified as the threshold, and if it's below the threshold when we've made it into a grayscale image, put it to black. So we have a couple different options for neurons, and then we're optimizing for that within that. So just to show you again, we've taken our color image, we've changed it using the script into a grayscale, and then after, this is the output of that neural processing, right? Making it into a solid black and white. And this is using the OpenCV library within Python. And using an adaptive Gaussian thresholding to reduce noise, which essentially just means that we're looking around each pixel to try and identify if the pixel is in a shaded region or in a bright region, so that we're not getting false positives for something being melted just because it's in shadow, because these are three-dimensional objects. It's using a really simple, essentially single layer neural network based on the concept of perceptron. And there's no backpropagation, no dependencies between them. So what that means is essentially what a perceptron does is exactly what that function is. It takes something to 1 or it takes it to 0 based on a binary classification function. So anything that comes in, it's going to make it white or it's going to make it black. And that's it. So we have a couple different functions that are doing that, making things white, making things black, and then we're bringing that into a single output. So our stream of data coming in is a single data source. It's all those pixels of data over time, and then those are each running through this binary classifier function, and we have a couple different thresholds, which is where it gets a little bit more interesting, and then we go to our output of the black and white image and drawing essentially a line along the edge of where the black and the white meet. So we were pretty excited about that. Didn't take nearly as long as we thought to get something like that up and running. Essentially we were like, okay, so we're able to take this input stream from our video, process it, and have an output, and that's great. We also have sensors within that that are doing temperature readings from our pointillist network. Let's integrate that, right? That seemed like a pretty straightforward thing. It should be just as easy, but it turns out actually going from one stream of one type of data to adding in multiple other streams of data is much more complex. So the first thing, pretty simple, pretty straightforward. We got you. Next thing, all of a sudden, skyrockets in terms of complexity. And that's one of the things that we are very much still in the learning curve at KieranTimberlake and in AEC more generally, is understanding which of these things are that couple of minutes, couple of hours, couple of days type problems, and which of these things are the 5-10 year problems. So when we realized how complex that was going to get, we decided that instead what we were going to do is we were going to look at people who have already done a lot of studies of temperature. So temperature is something that you get a lot of data pretty quickly because you're just taking temperature readings over time. And for us in particular, in our office, and you've probably heard lots of things about our test bed of an office at this point, we have 300 some sensors up around our office that are taking constant readings of temperature and relative humidity. And then we also have a survey that takes qualitative information from all of the office users saying, are you hot? Are you cold? Is it too dry? Is it too humid? So on and so forth. So we decided we would take our data sets and try and simulate based off of the study that someone else had done. Admittedly, theirs was in simulated temperature in an energy model. Ours is in real temperature in a real building. So there are definitely differences. But using some of their structure to then be able to structure ours appropriately, learning from the people who came before us. So as I said, they've got data, we've got data. The data's relatively similar. Starting to think about multiple different versions of applications of machine learning. And that's part of why we picked that paper as the one to model our study off of. They did something that's called hierarchical clustering, which essentially helps you identify which variables are more closely related to each other. So that we could say, okay, is it more important that the sensor is at elevation of 5'5", or is it more important that its nearest neighbor is 3 feet from it, as opposed to, being more similar to the other sensors that are at 5'5"? Starting to also be able to do things like identify when is it getting warmer, when is it getting cooler, right? Trying to identify things like this middle graph here where you can start to see, okay, this is the warming cycle, this is the cooling cycle, this is where we're essentially holding steady. And it's not doing a perfect job of it, but it's starting to get a lot closer in terms of understanding the behavior of the system. And essentially what we're looking for is knowing something as simple as, do we open the windows or do we turn on the air conditioning? Based on the temperature expectation for the day, the forecast that we get from Weather Underground, should we be opening the windows, or is it going to be so hot that we need to turn on our cooling system? And what's important with that is that it is kind of the dog species question, right? We have two possible outcomes, and we just want you to identify which classification we're going into. Are we going into a kind of day where our temperature is going to be comfortable and okay if we just open the windows? Or are we going into the kind of a day where we want to start cooling the building? Because once we get to the point that it's warm enough that we know we need to start cooling the building, it's kind of too late to keep the temperatures within a comfortable range, right? And so it's really useful to be able to predict, okay, do we need to cool the building? Do we open the windows? When do we open the windows? When do we turn on our system? But that only works if the prediction is close enough, right? So there's a sense of, oh, it would be great if we knew we could predict exactly what temperature it's going to be, right? Within our data set. But as you can see on the overfit over here, that means essentially it'd be like, okay, well now you open the windows and now you close the windows and now you turn on the AC system and now you turn it off and then you're going to open your windows again and now we're going to open the windows and have the AC on at the same time and then we're going to flip-flop. Because it's trying to track every single data point. You're getting a lot of noise and it's actually not going to give you a really useful outcome. Similarly, this makes the algorithm less adaptable when it sees data that it's never seen before. So, we were training it on summer data because that's typically when we need to have our windows open or we need to have the AC on, and that question is coming up. But as we've all experienced this spring, sometimes the temperatures are not what we expect them to be. So what happens when we get one of those anomaly days? We need our algorithm to be able to adjust and adapt. So we're looking for a fit that's, reducing the amount of error as much as possible without being thrown off by the noise. And we did a couple different types of model to try and do this. One is something called multilinear regression, which essentially is statistics, right? We're doing a lot of statistics and we're playing with the fit of how do we best capture as many of these data points as we can by piecing together a bunch of different algorithms. And we found that we horribly overfit our data um, with this algorithm. If you look at the purple line, that's our prediction, the actual data that we were trying to test, right? So the yellow is the training data. That's where we showed the machine the entirety of the data set. We let it go back and fix itself and tweak those variables and stir up that big pile of algorithms until it got itself to the point that it thought it was great. And then we showed it the purple data, or the green line of test data, which is underneath it that you can't even see. But where the purple data is where we were training it, or where we were testing it. And that was giving it new data it had never seen before and making it do those predictions. And as you can see, it was hyper accurate. Which says that something went wrong in training, because there were some anomalies in here, and you can see, there's a little bit of deviation where those anomalies occurred, but that's not a useful thing. That's following every single little bit of noise. So the next thing we were trying is something called a multi-layer perceptron. This is one where we get those forwards and backwards passes. It's got a bunch of different neural layers in it. It's a lot less easy for us to be able to point to exactly what's going on within it. And these are the results that we got. Pretty good. You can see that predicted test data wasn't responding to all of the noise in our actual data. And part of what we had in our actual data that we are giving the model in the testing section is we had some points where we didn't have data in them. So they were just giving out a single value across time because the sensor network kind of, had a hiccup moment. And what we see is that actually here the machine is fixing for that. It is noticing that in its prediction, straight lines are not super normal. So it's starting to predict and say, okay, well, here's actually where the temperature should be going to, which actually in a lot of ways is more useful than being able to predict, oh, a sensor's gone out, it's just going to stay out for a while, right? So starting to fix some of that overfit. But this is one that takes a bit longer. So we looked at one other thing from the paper, which is the extreme learning machine, which essentially again, has a multiple layer neural network. This is simplifying it a little bit in the neuron calibration column there. The hidden layer actually has multiple layers of neurons within it, but it doesn't require the back propagation in the same way. It's called a feed-forward network. It's much, much more efficient in terms of processing speed. And you can see our output here. A little bit more noisy than the MLP, the last one that we looked at that had the back propagation, but still reasonably decent. So what did we end up going with? Well, this was a little bit too much noise, right? This is the open the windows, close the windows, open the windows, close the windows type model. And so we decided to go with the MLP as the multi-layer perceptron as the model that we were actually using. So taking our input from our point-of-list sensors, and then the goal being that we're now integrating output from Roast, which is one of our beta products right now, that does post-occupancy evaluation surveys that ask you, how comfortable are you? They optimize, it asks you for that qualitative comfort data. And what we're looking at is, okay, we have all of this numeric data. We have temperature, we have forecast of weather, we have all of that stuff that we've been training on. But really what we want is to optimize the output in terms of people's thermal comfort and in terms of people's overall comfort. So that's a qualitative data stream that we would be integrating. And if you're interested in Roast, there's a great article that just came out by Fast Company, I think, or Design Intelligence, one of those. But if you Google for it, it's out there right now, and you can look into it more, or you can email me if you have any other questions and want to hear more about it. I can direct you to the project manager. So with that, let's chat. Let's talk about it. Let's talk about data. Let's talk about machine learning. Any questions that you guys have?